We're going to continue our discussion about ionic compounds and naming ionic compounds. This particular slide is still dealing with binary ionic compounds. The naming system, which we call the nomenclature, involves combining the names of the positive and the negative ions. So we combine the names of the cation and the anion. The cation, like I said yesterday, the cation will be coming first. We always put the cation first, the anion second. You're also going to see that the ratio of the ions is not indicated by the compound's name. Okay? It's not indicated by the name. It is understood because we know what charges that those particular compounds take. For instance, if you see the name calcium, okay, what charge is calcium going to take? What charge will calcium take? Positive, what? Positive. You might as well take out your periodic tables. We're going to need them. Positive 2. Because calcium is going to lose 2 electrons. So as a cation, it's going to be plus 2. Might as well take out your ion sheets also. You're going to need those. If you look at any of the halogens, okay, we don't need to put the charges in the name because we know chlorine's going to have what charge? What charge is chlorine going to have? A -1. Excellent. Okay, so these charges are not represented in the name of the compound. It is understood. So, very first example that we are going to work, SrF2. My cation is first, my anion is second. So as I am looking at this, what is Sr the symbol for? Strontium. So I would just simply write strontium. What is F? Fluorine, correct? F is fluorine. However, remember, when we are dealing with the anions, we have what kind of an ending? Ide. So I need to change that INE to an IDE. So if I'm naming this particular compound, it is strontium fluoride. That wasn't too tough, was it? That wasn't too tough, but believe me, it gets harder. Here's another one. ZNO. What's Zn? Zinc. O is oxygen, right? However, we have to have an IDE ending, so this is going to be oxide. So we're talking zinc oxide. Nice and easy. However, there's got to be a rub. Here's the rub. Okay? Nice and easy, but the rub. The rub is the stock system of nomenclature. Some elements form 2 or more cations with different charges. To distinguish which ions are formed, the stock system of nomenclature is used. Now, look at your ion sheet. Flip it over to the side that has the periodic table on it. Find, let's say, iron, Fe. If you look at iron, it says that it has a 2+ charge and a 3+ charge. Right beside it, cobalt, 2+, 3+. Okay? Look over a couple more at copper, Cu, 1+, 2+. Couple down from there and over, lead, Pb, a 2+ and a 4+. These are all cations that have different charges. You need to use the stock system of nomenclature when you have these particular ions. Now, these are cations. We will always use the stock system, okay, on the cation. Well, I guess that's not totally true because we'll use it on molecular bonding later on, okay? But we don't put, okay, and I'll show you here in a second, when we're dealing with ionic bonding, when we're dealing with formula units, we do not put a Roman numeral on the anion, only on the cation. So we're going to use Roman numerals to help us distinguish which one of those ions we have. Just like I said, iron. Iron has a 1+ charge, or excuse me, a 2+ charge. Iron also has a 3+ charge. So if I'm signaling iron 2, I have a Fe 2+. If I have iron 3, I have an Fe 3+. So those Roman numerals indicate the charge. Now, the names of metals that commonly form only one cation do not need Roman numerals. So, if they only form one cation, we don't use a Roman numeral. If you do use a Roman numeral, it is not correct. So, aluminum only takes a 3+ charge. It does not need a Roman numeral. Barium only takes a 2+ charge. It does not need a Roman numeral. Sodium only takes a 1+ charge. It does not need a Roman numeral. Now I'm going to show you an easy way to determine whether something needs a Roman numeral or not. I want you to look at your periodic table. On your periodic table, above the symbol, there is a little black number that says oxidation state. Find that number. Find that number. I want you to find the oxidation state for sodium. What is it? Okay. Sodium is what? +1, right? So, is there more than one tiny black number there? Then I'm not going to need a Roman numeral. Now, we talked about iron. Iron 2 and iron 3. I want you to find iron. What are the numbers above iron? +2 and +3, right? So what charges does iron take? +2, +3. So if you look on this periodic table, and you see more than one of those little black numbers, you are going to need to have a Roman numeral. Look at chromium. Look at chromium, element number 24. What is chromium's numbers? +2, +3, +6. So that chromium right there could possibly take a +6 charge. So you would need a Roman numeral 6. What's Roman numeral 6? VI. Okay? VI. What is IV? 4. Good, good. Well, let's look at some other ones. Okay? Look at tungsten down there. Element number 74. How many different possible ions could tungsten have? You have +2, +3, +4, +5, +6, all of those. So you would need to have Roman numerals for those. Now, look at, let's say, silver. Find silver. Does silver need a Roman numeral? No. What if you put one? It's wrong. Okay? Look at scandium, number 21. Scandium need a Roman numeral? No. What if you put one? It's wrong. Okay? Look at cesium, number 55. Does cesium need a Roman numeral? Nope. What if you put one? It's wrong. Look at tin, element number 50. Does tin need a Roman numeral? Yes. Okay? Yes. Look at chlorine, element number 17. Does chlorine need a Roman numeral? Trick question. Chlorine is an anion. Do anions need Roman numerals? No. No, they do not. Okay? So don't get confused. That was a trick question. Seeing if you're paying attention. Because I just said don't put a Roman numeral on an anion. Only the cations. So, okay? The reason is right here, folks. There is no element that commonly forms more than one monoatomic anion. Now, you looked at chlorine there. Did chlorine have multiple oxidation states? Absolutely it did. Okay? However, when we're making an anion, when chlorine is gaining or losing electrons, what does chlorine do? Forming an anion, what will chlorine do? It will gain one electron, always, to fill its outermost energy level. How about oxygen? How about oxygen? Oxygen needs 2 electrons to fill its outermost energy level. So when oxygen is an anion, it's always going to be 2-. Okay? Does oxygen have more oxidation states? Actually, no, it doesn't. Okay? Now let's look at this guy right here. Go ahead and write this down and we'll work it. All right, let's roll here, folks. CuCl2. What is Cu? Copper. Okay? So, name of the cation is copper. Does copper need a Roman numeral? How do you know copper needs a Roman numeral? There are two oxidation states above copper. What are the two oxidation states? 1 and 2. So I could have a copper 1 plus charge or a copper 2 plus charge. Okay? So I do need a Roman numeral. Now, how do I figure out whether I have copper 1 or copper 2? Okay? How do I figure out whether I have copper 1 or copper 2? Well, I know that my charges have to balance out, don't they? My net charge needs to be 0. Do I know the charge of chlorine? What's chlorine's charge? -1, right? So how many total negative charges do I have in this particular one? How many chlorines do I have? 2 chlorines. Each one is what? -1. So what's my total charge? -2. So my total charge for chlorine here is -2. How do I get that equal to 0? Obviously, I need to have a +2. So what what copper am I dealing with here? 2. So I'm going to write copper 2 chloride. Copper 2 chloride. Now we're going to talk a little bit about Latin names. Okay, a little bit about Latin names. Now I put this slide on here because you are going to see some Latin names. Have you ever thought of why that copper is abbreviated Cu instead of Co? Okay, well, number one, cobalt's Co, but Cu comes from its Latin name, cuprous and cupric. Now, if you look on the ion sheet that has the periodic table on it, right below that, you are going to see a bundle of these. They call it classical, the classical system, which is using the Latin names. Chromium, chromus, chromic. Cobaltus, cobaltic. Ferrous, ferric. You ever thought why iron is Fe? Ferrous, ferric. Now, the OUS represents the lowest charge. The IC represents the highest charge. So if you would see something that said ferric on it, what would ferric be? Iron +3. Okay? What would stannous be? Stannous would be tin2. Okay? We don't use them often, but you will see them. So you have to be aware of these Latin names. Okay? I have here that says click here. Let's see where this takes us. Oh, it's going to say something. I don't know what. Oh, it's saying it could be poisoned. Okay. Right here, I have just another table that has some more of those. Okay. Some more of those. And if you ever wonder why, you probably can't see this in the back, but if you ever wonder why, you know, something like gold. Why is gold Au? Okay. Well, because of the Latin name Aurum. A-U-R-U-M. That is gold in Latin. So that is why gold has the Au. Okay. Now, I think my next slide is going to talk about some polyatomics. Okay, so have PAL out. Have PAL out and handy. Polyatomic ions. Now on PAL, your polyatomic ion list, you can look at the endings of all those words, and you're going to see three of them. You're going to see the IDE ending, rarely. Most of them are going to end in ATE and ITE. The most common of those anion, or excuse me, of the polyatomic ions, the most common one will be given an ATE ending. And then it's all about the number of oxygens. Okay? If you look, nitrate, the nitrate ion is NO3 minus 1. One less oxygen than that, NO2 minus 1, is going to be the nitrite ion. Nitrate, nitrite. We also have hypo and per. Hypo and per, and this is a very important slide here, folks, so I would copy this exactly. This slide right here is showing you, and this is on your PAL. Okay, so when you need to remember this, just find chlorate on your PAL. So find chlorate. Okay, find chlorate on PAL. ClO3 minus 1. Okay. If you have one more oxygen than chlorate, so if you have ClO4 minus 1, we call it perchlorate. One oxygen less than chlorate is chlorite. One oxygen less than chlorite is hypochlorite. Okay, hypochlorite. Now, the only thing that this slide is saying right here, okay, the only thing that this slide is saying right here is that if you're using polyatomic ions, you need to have parentheses around them.